Now let's use the ideal gas law in two different ways, because the ideal gas law is incredibly useful in that it's the gateway to a lot of other formulas. These two other formulas are molar mass of a gas and to solve for the density of a gas. I'll show you how to derive the formulas. I think when it comes to a testing situation, you can always just put these particular formulas on your note card and just be done with it. If you just decide that you can derive them during the test, or then you should totally feel free to do that. But I will go ahead and show you where these formulas come from. So let's go ahead and solve for the molar mass of a gas formula. Know that in both cases, for the molar mass and for the density derivation, we're going to start with PV is equal to nRT. So molar mass, as a definition, is the mass of a gas sample divided by the number of moles of a sample. And we know from PV equals nRT that mass over, we're going to rearrange PV equals nRT to solve for n. N is going to be PV divided by RT. So I'm going to put PV over RT in the denominator. So P over V, or PV, sorry, divided by RT. So I have this formula here, mass divided by P times V, which is also divided by R times T. So we're going to simplify by putting the RT up on the mass side. So this is mass times RT divided by PV. So now I've got a decent formula for the molar mass. If you're given the mass of a gas, then this is the formula that I'd pick. Um, However, if you're feeling slick, you might realize mass over volume is actually density. So if in a problem you're given the density of a gas right out, you can simply use this other formula. So D, which is mass over V, times R times T divided by P. So as a matter of fact, there are two new formulas you can get from the ideal gas law if you're trying to solve for the molar mass of a gas. I think they have different utilities. So if the problem gives you the mass and gives you the volume, you just use the first formula. You could also just solve for the density of the gas and then substitute that density in for D and then solve by using D times R times T over P. So in a similar way, let's solve for the density of a gas formula. Density is mass over volume. Well, volume is also in PV equals nRT. Volume is nRT divided by P. So I'm going to replace volume by nRT divided by P. So just like I did with the molar mass derivation, I'm going to simplify the appearance of this formula and multiply mass times P and then divide that by N times R times T, that by N times R times T. And then actually also similarly to what happened right over here, mass divided by N is molar mass. So actually the density of a gas is equal to the molar mass of a gas, that's molar mass, times P divided by R times T. So if you know the identity of the gas, like if, for example, I tell you that it's carbon dioxide or it's carbon monoxide, you can solve for the molar mass and just place it in this formula and multiply it by the pressure, divide by the product of the corresponding R value times T expressed in Kelvin. So in our last two slides here, we're going to do one problem calculating molar mass, and then my last problem will be calculating density. So calculate the molar mass of 2 grams of a gas which occupies 10 liters at STP. So there are two forms of that molar mass formula. The first is mass times RT divided by volume times P. So molar mass is equal to the mass, which is given as 2 grams. Now, again, when it comes to R, since you're not told which pressure units to use for STP, it doesn't really matter. So let's use kPa. So we're going to use 8.314 liters times kPa over moles times Kelvin. It is standard temperature, so we're going to use 273 for Kelvin. And then Kelvin's cancels out right away. Divided by the volume being 10 liters. And the standard pressure, since we are using kPa, is going to be 101.325 kilopascals. So kilopascals will cancel, liters will cancel. So we will end up with grams over moles, because moles is actually in the denominator of that gas constant unit. So molar mass will be the answer for this work once we work it out. So 2.00 times 8.314 times 273, all over 10.0 times 101.325, and I get 4.48 about. Three significant figures, so 4.48 48 grams per mole will be my final answer. Of course, the other way to do this problem would be to use molar mass is equal to dRT over P. Just realize that your work is basically going to take the same form. You'd have to solve for density first. Density would be 2.00 grams divided by 10.0 liters, since density is mass over volume. So the density of this gas is 0.2 grams per liter. By the way, gases, like, as a whole, have very small densities. So don't expect the densities of any of these gases to be huge. So in this last problem, let's calculate the density of fluorine gas at 770 torr and 10 degrees Celsius, which is, by the way, not STP, just noting that. So density is equal to pressure times molar mass divided by the product of R times T. So pressure is given to you as 770 torr. And you'll have to multiply that by the molar mass of F2. Molar mass of F2 is 37.996. Don't worry about the units, they will work themselves out. R, since we are using torr, is going to be 62.4 liters times torr divided by moles times K. All that is multiplied by the temperature, which should be in Kelvin, so this will be 283 Kelvin. So kelvins will cancel. Our moles will cancel. This moles will cancel with that moles. Torr will cancel. So we're going to end up with units of grams per liter for our final answer, which actually makes perfect sense. So when you threw this in your calculator, you get 770 times 37.996 divided by the product of 62.4 times 283. And I get 1.6567, something like that. Just write down a bunch of decimals first. 6567 grams per liter. Significant figure says 3 sig figs, so density is going to be 1.66 grams per liter, which is a pretty small density and which makes total sense for a gas. So I hope this screencast helps you work out ideal gas law, understand the concept as well as the practice problems. Please reach out if you have any questions. See you later.